I'm not disconnected nothing. Okay, so we have this equation. Set this equal to 0, and we get, this is determinant, of course, and we multiply out the diagonals and so forth, and we're going to get this, okay? And the solutions are going to be 4 and -1. So the solutions are very easy. It factors into lambda plus 4, or -4 times lambda plus 1. Set each of those equal to 0, etc. We certainly know how to do that. Okay, so then for each of those solutions, we solve this, and everybody says they got a solution. I didn't look over your shoulder. But there we have. Okay. I'm also disconnected. It's master. Okay. So we want to solve this equation. Well, this equation for lambda equals 4. Now we can solve this, and we don't necessarily have to go to simultaneous equations and augmented matrices. We do a matrix operation here. It says not to confuse it. We'll save that for a few minutes. We'll just write out the simultaneous equation. You get x plus 3y equals 4x. And you get 2x plus 2y equals 4y. Okay. This gives you a homogeneous system. You subtract the 4x from both sides here, you subtract the 4y from both sides here. Then you get -3x plus 3y equals 0. So that x had better be equal to 1. Okay. And you get -2x plus 2y equals 0. Well, it has the same solutions. Actually, the same equation. If you just multiply this by 3/2, you get this. Or 2/3 this equals this. Okay. Okay. Often we'll do this as an augmented matrix, and okay. If I have written this as an augmented matrix, it would have been the matrix -3, 3, -2, 2, 0, 0, which reduces down to 1, 1, 0, 0, 0, row 0. Same thing. Just make sure we understand these connections. So that let y be your free variable. Let y equal t. And x equals t. And your solution is t. Everybody real clear on those steps? And putting it into the terminology of augmented matrices. We've got this. Which of course equals 2 times 1, 1. Okay, well, the book doesn't do a lot with the geometry here. but I think the geometry is really important for intuition. So I'm not disagreeing with the author. He does a wonderful job, beautiful presentation of all this stuff. It's very well done. Okay. But I prefer to talk about the geometry right now because it makes sense out of things in a way that a lot of other stuff does. He shows you all the operations, the theory and everything. So you're going to see that. And you're not going to see the geometry of it right away. What this is a transformation of R2, right? Okay, so what we know then is that your matrix I say is a transformation. I should say it represents a transformation, but I didn't have room to write represents. Okay. It represents a transformation from R2 to R2, which we can illustrate. Okay. And so here we've got R2, and here we've got the vector 1, 1. This transforms over here into the vector 4 times 1, 1. If you plug in 1, 1 here, you're going to get 1 times 1 and 3 times 1, which gives you 4 times 1. So your x is going to be 1, except your y is going to be 2 times 1 plus 2 times 1, 4 times 1. Okay. So that the vector 1, 1 transforms over here into the vector 4, 4. You notice that 4, 4 is in the same direction as 1, 1. Meaning, and then if this was t, whatever t is, right? So it's some vector longer than this or shorter than this, and maybe back in this direction because t could be negative. Okay, so if you take any vector t with equal x and y components, whether positive or negative, you get a vector along this line. And your transform vector is going to be along this line. It's going to be 4 times as long. This means you're stretching your plane by a factor of 4 at that 45-degree angle. Now that's important for the visual, and it's worth talking about before we even give a name to this. That name is eigenvalues and eigenvectors. Okay. All right. Now the other solution, and I'll just kind of lambda equals -1 gives us the matrix 0, 3, yeah. No, sorry, that's 0. It has to be something to get down here. And so like when I subtracted -1, I just subtracted 1. It's really easy to do that. And that's fine. Okay. So we get the matrix 2, 3 times xy equals xy. And that gives us the augmented matrix. I'm sorry. 2, 3 times x, y would be 0, 0. Why? That gives the augmented matrix 2, 3, 0, 2, 3, 0, which gives us a matrix of I'm going to use I'll use 1, 3 halves, 0, 0, 0, 0, so that your solution, you have a free variable again. We don't want to call it t because we already used t. So the free variable we'll call s. Okay. Just leave myself enough room. Okay, for y equals s equals x equals negative 3 halves s. This is house wiring. Just a simple. Corollary of what we're doing in physics. Okay. Goal is not house wiring, goal is understanding electric magnetic field, which is going to be a real adventure for you in a year. Okay, something to look forward to. Okay, well, anyhow, down here, we get y equals s, x equals s, so we can say x, y is s, s, negative 3 halves s. So we could do s times negative 3 halves 1. Well, s is an arbitrary constant. And this is equivalent to, well, let's just let s be twice as big, then we get a negative 3, 2. Which of course we could have gotten out of this pretty easily. Okay. I'm just going to write that without comment. It's a multiple of this, and a multiple of this is a multiple of this. It just be a little different. Okay. Well, what's this tell us? It tells us that the vector negative 3, 2, and it's kind of inconvenient. That's where I labeled this thing. I thought it had a little better. My label for the negative 1, 1 for the 1, 1. Here. Negative 3, 2. Well, we come over at negative 3 and up 2. So here is negative 3, 2. Now, how does this transform? Well, if I multiply this matrix by negative 3, 2, I get 1 times negative 3, and which is negative 3, and 3 times 2, which is 6, which gives me 3. Okay? And multiply it, and you can do it yourself. Multiply this by negative 3, 2, I get 2 times negative 3, okay? which is -6, and 2 times 2, which is 2, excuse me, 2, negative 2. Okay, -6 and 4. I said 2 times 3 is 2. 2 times 2 is 4. Okay, -6 and 4 is -2. Okay, the point is that this maps then to 3, -2. Okay, and it's no coincidence that 3, -2 is just -1 times -3, 2. Because the equation we solved was this should equal lambda times whatever your vector is. Okay, if your vector is -3, 2, you'd better get 3, -2, -1. Okay, and again, my leg one is, well, no, I don't. So the vector has the same length and the same direction, it's just in the opposite direction. Or say it's parallel. It's on the same line. So here we have 3, -2. And everything is along this line. Right. So along this line, we're stretching things out 4 times as big. Along this line, we're reversing. Okay. Okay, well, let's take this just a little further. These two vectors, 1, 1 and -3, 2, form a basis for R2. And over here, the transform vectors, of course, form a basis for our transform space. This base is V. This base is W. And we have a basis for each space with the convenient property that this basis vector is just a scalar multiple of this one. And this basis vector is just a scalar multiple of this one. Meaning that the matrix for our transformation is going to be very simple. Let me just write that out. Okay, I've got to rearrange space again. It's going to be dangerous. Okay, so the upshot of this is if the basis for V is 1, 1 through 2, the basis for W is 4, 4 through -2. Call this matrix B, or this basis B, call this basis B prime. And the matrix for the transformations in terms of B and B prime is what? Okay. Well, think about it. This matrix multiplied by the vector 1, 1 is 4, 4. What's that tell you about the matrix? And what does it tell you that multiplying this matrix by 3, -2 equals -3? So what numbers we have to put into this matrix? Think about this for a minute. Okay, I apologize, I screwed that up. Okay, in terms of this basis B, the vector 1, 1 is the 1, 0 vector in terms of B. Okay, because what does 1, 0 mean? Well, what is x1 or what is x1, x2 mean? Or C1, C2, okay? C1, C2 means C1 times this plus C2 times this, right? And if we want just this, then C1 has to be 1 and C2 has to be 0. So in terms of B, we have this. And okay. So in terms of these two bases, we would say this, okay? And well, in that case, the matrix would have to be, well, it could be 1 anything and 0 anything. You gotta have a 1 here to get a 1 here. It doesn't matter what you have here and here, it's going to multiply by 0. Okay. Down here, you would have to have 0 here and 1 here. It doesn't matter what you have here. 0 multiply 0. 1 would multiply 1, which would give you your 1 here. Okay. So what you end up with is just the identity matrix in terms of these two bases. Now, in terms of the standard basis, the matrix is, of course, the one we started with, but I don't have up here anymore. But it's your 1, 3, 2, 2 matrix. Matrix you started with in order to do all this. Okay. So anyway, let's go ahead and develop this. What we've seen is that this matrix transforms this vector to this vector and this vector to this vector. Stretches space this way and doesn't stretch it in this direction, but flips it. Okay. Now, it's called the eigenvalue equation. And in general, the eigenvalue equation is this. for matrix representing a linear transformation, an n-by-n matrix transformation of a space into itself. There's your Eigenvalue equation. Well, let's see where we get this. 1 minus lambda and 2 minus lambda and all that stuff. Where's that from? Well, lambda x is the same as lambda times ix. So we could write this equation as ax minus lambda ix equals 0. So a minus lambda I times x equals 0 because it's properties of matrix multiplication. It's distributed. So we can factor out that x essentially. By the distributive law, this times x is ax, which is here, minus lambda ix, which is here. Now, if a equals three, two, two, isn't it? 1, 3. Okay. Well, what's lambda I? Well, I is your 1, 0, 0, 1 multiplied by lambda, you get lambda 0, 0, 7. And then when you do the arithmetic, you do 1 minus lambda, 3 minus 0, 2 minus 0, 2 minus lambda. And that should be very straightforward. Which is the equation I started with. Well, it's not the equation I started with, but okay, now a minus lambda I equals 0 means do you want to say that? I guess. Put X in there. I'm not going to write it out there. You know what the equation is. A minus lambda I x equals 0. That's correct. I'm sorry. Has a unique solution. If determinant of A minus lambda I is not 0. because that means the matrix would be invertible, and if we multiply both sides by the inverse of A minus lambda I, we're gonna have an inverse matrix times 0, which is gonna give us a 0 vector, right? Well, that's not gonna help give us a solution to this equation. I mean, the 0 vector is always a solution to this equation for any lambda. So that's not even interesting. What's interesting is solutions exist for lambda if and only if determinant of A minus lambda I is equal to 0. Since if it's not equal to 0, it's invertible and you get nothing, right? Only trivial solution. Just like this one here. Okay. I'm just going to say, if we solve this equal to 0, proceed as in the example. Because of course, to make the connection that's there, this is just what we did. And the reason we did it was so we could see this thing about the structure of this transformation in R2. That would stretch everything this way and flip everything along this way. And everything else follows according to that basis. Okay. Okay. Now, look at the board page here. We call lambda an eigenvalue. The vectors I can't read all that, but you can see it's eigenvectors. Okay. The span of the vector 1, 1 is its eigenspace. Now that's just a diagonal line in this case, because this is just a two-dimensional. Example, okay? If you're in higher dimensions, things can happen, okay? Your book has examples, so I'm going to kind of outline those without going through all the details, okay? Well, I'll show you some. Matrix representations that will give you, for example, okay, when you do this in higher dimensions, solving this could give us repeated roots. Now your book does a real simple example. Okay, they have a lambda minus 2, lambda minus 2, lambda minus 2 on the diagonal of 3 by 3 matrix. And then they have a couple of other numbers. It's upper triangle. And when it's upper triangle, the determinant is just the bulk product of the diagonals, right? Okay. If you're familiar with that, that's something we've seen. Might have lost track of it because we haven't talked about it recently, but it's pretty obvious. So make sure you understand why that is. And what you get is you get repeated eigenvalues. Okay. Your determinant is lambda minus 2 cubed equals, and that's equal to 0, so lambda equals 2. And there are 3 solutions. Lambda equals 2, a repeated solution. And that's just about the geometry, because then the eigenspace corresponding to the eigenvector that you get for that repeated eigenvalue is going to have multiple vectors. So your eigenspace can be spanned by more than one vector. So if you got an eigenvalue of 4 or 2, in case of example your book gives, and you plug 2 in to this 3 by 3, okay? I'm waving my hand on this, we'll write it out. I'm just going to give you an idea what eigenvalue, eigenvector, and eigenspace, how they're related. Your matrix could reduce to one with 2 rows of zeros. So you have 2 free variables. Each free variable would give you a different eigenvector. So lambda equals 2, plug in, this is a 3 by 3. It's perfectly possible that everything reduces down. You have only one row that's non-zero. So you have 2 free variables giving you 2 different eigenvectors. Okay. Then your eigenspace would have dimension 2. In 3-dimensional space, that would correspond to a plane. You get 2 vectors, both in the eigenspace, so any combination of in the eigenspace. So eigenspace is a plane. Okay, well, talk about the geometry a little more than the book does, but it's important stuff. Okay. Okay. If now let's go back to our example. Okay. I use negative 3. Okay, if we use the same basis for both V and W, transforming from R2 to R2 again. Let's go picture. Notice where we are. And so here's our picture. Now over here, well, we didn't do it here, we did it somewhere else. We used different bases over here than we did over here. We used these vectors for the basis here, these vectors for the basis here, and we got the identity matrix. Okay. I'm going to use the same basis for both spaces. Transformation represented by this matrix relative to the standard basis is now represented by A prime for A prime music. You know what happens if there's music in the background? I do find it distracting, but even worse than that, it makes me want to dance. Not sure how you dance to that, but I'd find a way, and it wouldn't be pretty. You'd probably never look at dance again if you watch me dance to whatever the music is. Okay, so I'm going to have to pull the door. Okay. No objection. That's important for the lesson over there. And to reward myself for not dancing. Your sanity is enough reward, but I'm going to get a new piece of salt. Okay. Okay. So here we are. And we got this relative to the standard basis. That's our transformation. And it looks like this. We're going to represent it by A prime. For A prime times 1, 1 equals 4, 4. And A prime times negative 3, 2 equals 3, negative 2. I'm going to ask you to tell me what that matrix is. Okay, I seem to be unable to say what I mean. I'll just rewrite this erase. Relative to this basis, okay, the vector 1, 1 is the vector 1, 0. the vector 1, 1 is 1, 0 according to this basis. It's 1 times this plus 0 times this. It takes this to 4, 4, which equals 4, 0 with respect to B. Okay. Because 4, 0 with respect to B means 4 times this and 0 times this. Okay, what else does it take? Well, it takes also it takes negative 3, 2 to some matrix relative to B. And well, what's this matrix relative to B? What's this matrix relative to B? You fill in the blanks. Just make sure you understand. Okay, some of you got it, some of you have got it, some of you didn't quite get it. Okay. So just make sure we understand. Negative 3, 2 is how many of these plus how many of these? How many of these do you need to get negative 3, 2? Well, how many of these do you need? You need one of these, right? Okay. How many of these do you need? You don't need. Okay, so this would be 0, 1. And let's write a little explanation because we want to make sure everybody understands. Well, let's do this. And I don't really have room to write an explanation. Okay. So what's 3, negative 2 relative to B? What would you multiply this by and what would you multiply this by in order to get 3, negative 2? Well, 3, negative 2 is just a negative of this, right? Okay. And that would be 0, negative 1. I'll write the clouds here. So 0, 1 relative to B. Well, let me make it more general. I'll write what I was about to write, but first I'm going to put it in bigger context because what's D1, D2 relative to B? This means D1 times 1, 1 plus D2 times negative 3, 2, right? Okay. So essentially, if we're trying to say that negative 3, 2 equals something with respect to B, we got to find a D1 and a D2 that give us negative 3, 2. Well, clearly that's D1 equals 0 and D2 equals 1. So that means D1 times 1 plus D2 times -3 2 equals -3 2. And the obvious solution is D2 equals 1. So we could formally write this out. But of course, in this case, this is just a multiple of one of these two vectors. And it turns out the multiple is just 1 times that vector. Okay. Then, as we saw down here, to get 1 0 b, which represents 1 times this plus 0 times this, but this goes to 1 0 to get the next vector 4 4. Well, that's just 4 times this. Okay, so the whole point now is if you have eigenvalues, it's really easy to write these representations. Okay, so what matrix does this? Okay, what matrix multiplies 1 0 b, which represents the vector 1 1, to get 4 0 b, which represents a vector 4 4, according to this basis. And also multiplies 0 1 b, which represents your -3 2, to get 0 -1 b, which represents 0 and negative of -3 2, which is 3 -2. Okay. So we set that matrix up. Okay. So what's your matrix? Okay, I'd like to give you a little more time on this. We've got another class that we do. I think we're about out of time. Okay. What you get here, you have to have a 4 here, multiply the 1, right? Okay. And you have to have a 0 here, multiply this one, that's what's going to give you 0 here. It doesn't matter what you have here and here because these numbers are going to multiply 0. and they're gonna give you zero, okay? So it's kind of like you got this and then something here, but the something here and here, you get by saying, well, I don't know. And for this equation, what's here and here, but I'm gonna have to have 0 and -1 here. Okay, can't have anything here, but I've got to have 0 here. Because if I didn't, I'd get something besides 0 here. Okay, well, I think I understand the logic of that. Okay, so what it comes down to now is we know what these asterisks are. Okay, I have to have 4, 0 to make this so. I have to have a 0, -1 here to make this so. So my matrix is 4, 0, 0, 4. In both cases. Well, what's 4 and -1 have to do with anything? Those are the eigenvalues we got for our original problem. So comes down to this. You're going to get a diagonal matrix. This would be in any n-dimensional space. In 2-dimensional space, it's just λ1, λ2, right? So we identify this, you know, that this is this. Provided your eigenvalues are distinct. That means they're all different. And that's what the 2 sections you have for homework next time are all about. Now, the examples, you should be able to understand the examples and the explanations in terms of this one example that we've used to show most of the mechanics. The picture that goes with this, of course, is you have transformation from one space to another defined by vector A. And up here, you have this diagram. The A prime comes by using the eigenvector basis. Okay. Just to relate this to what's just homework for this time. You got your basis B up there, standard basis here. And B is eigenvector basis. Okay. That's the big picture.